show you the laser pointer.
They did,
you point at that.
Point at that, and so we can y'all see that? Excellent, all right.
Excellent.
I'm trainable, despite my wife's claims. Okay, y'all, very excited to be here today at the University of Arizona. I want to thank Liesl and Zoffer for the invitation to come and talk to this really amazing community in this really critical location. So today, I'm not going to use, I hope, all 1 hour and 10 minutes. Hoping to keep this a little shorter and then invite some questions, and I'll answer anything I can. And then maybe we can break a little early and spend the time networking with each other. Please call me Todd, and so let's get started. First, this is sort of my equivalent of the Wall Street disclaimer you might see. I am on the Industrial Advisory Committee, but the views that I'm presenting here are those of SRC and my own. It's important to understand that on February 9th, the NatCast organization that is going to be administering the National Semiconductor Technology Center, or NSTC, let's call that a Semitech 2 just for a lack of a better concept, has committed $5 billion of the CHIPS R&D funding for 5 years. And I have complete confidence in Deirdre Hanford, who is now the CEO of that, and the amazing board of trustees there. If this community is interested, there is a community of interest link on the NatCast page where each organization can sign up and get involved. They want to hear from you as they start to organize what the technical efforts are going to be and what membership and participation might be like. So register. Okay, so it's obvious to this group that the CHIPS Act has been about manufacturing, and I'm thrilled to say that that manufacturing initiative is starting to take root. If you didn't see it, Global Foundries received a green light for their investments this morning. And the White House has a nice map of the manufacturing initiatives that are coming online. There's a couple things here in the middle that I want to point out. One is that 12 of the companies make up over 90% of the committed investment. All of those companies I work for, right? So I am constantly getting perspective on what the different geographics need, what the technologies need, what the people needs are. And so I put a list on the right. The other thing to point out is there's a lot of gray dots on that map. And those gray dots are in other technology spaces, in batteries, in bio. But semiconductor is still capitally intensive, and it's going to be just a couple key locations, and it's going to be huge financial bets. And so this generational shift is coming to America, and we need to meet it with technology, we need to meet it with people, and Arizona is going to be a key part of that, which is why I put this little heart down here. So. Now, y'all know this because every day you wake up, you see something on the news, you read a paper. Some of it's good, some of it's maybe not as good as it needs to be at this moment in time. But, you know, TSMC was really a catalyst. They are an amazing company. I'm proud to have them as a member. They're far more humble than they should be. They're hardworking. And bringing them to America is a lot like bringing Mercedes, BMW, or Toyota to America and welcoming the best and the brightest to help our economy and help make parts, and to step up the game of maybe some traditional American companies that need to step it up. And so Joe was here not long ago, President Biden, and celebrating these investments. And there was a really nice piece just the other day about how this is really reinvigorating some of Arizona's local economy. So today I hope to tell you a little bit about what SRC is. We're not a household name. And importantly, I need to help you understand what we're doing today versus what our ambitions are. I'm going to share with you what I call our 3 pillars for the decade, or 3 Ps, and that is prosperity, the people, and the planet. So if you leave with nothing more than there's 3 Ps, at least be solving 2 of those, then you've passed this class. I'm going to share with you my view of the R&D pipeline for semiconductors, and then dig into the technology that we talked about with the decadal plan, which is the systems that need to be built, the Microelectronics and Advanced Packaging Technology Roadmap, which was commissioned by NIST, and is how to do that in chips and packaging with a workforce emphasis. And now really the hope is that the implementation comes from the CHIPS R&D office. I will dig into low dimensional materials. I was a chemist, organometallic chemist at one time. I do love materials, and I'm trying to find a way to reinvigorate the materials and mechanical engineering love for semiconductor making. And then finally, talk about workforce and education, where the goal is really to inspire the next generation, because we've lost their hearts and minds with the narrative of faster, cheaper, smaller, throw it away. So let's dig in. I am only the third CEO at SRC's 42-year history, and I love this job because it's not complicated. We need more investments in science and people, period. So my job is to make it as easy and as lean in an overly bureaucratic, legally dominated world to make sure the money is flowing to those ideas and to the students, whether they're young or returning to the lifelong learning adventure. We are neutral, trusted, and science-driven, and have given over $2.5 billion in investments and essentially supported over 15,000. We call them SRC scholars because we want to pursue scholarship. I will say I've driven over $500 million, and I feel like it's still the status quo and I've done nothing. So if you hear me say that I'm failing, it's because even $500 million is not moving us fast enough. So really thrilled with Liesl and Zafer's note to come out here because Arizona gets it. Arizona Commerce Authority is making investments that are helping to accelerate the contribution to this space for driving the development, driving the research ideas, taking some risk. Not all that's going to work out, and then supporting the people. And was really thrilled to see Christina, who I believe is at least partially supported by an SRC contract in this article. So how we work is pretty straightforward. We get together with government agencies. This should be 2. Not 3, sorry, and 26 member companies, and we define what is a meaningful agenda for you and your organization that we can collaborate on with like-minded travelers, right? We are not a single program. We create programs that people want to travel with that are critical mass investments. If we don't get enough money, then that program doesn't go. If we don't get the right partners and they're not going to be good travelers for that program, they can't join that program, right? So that takes about 1 to 2 years, and we did hit $100 million last year. About 2/3 of that comes from support through a DARPA program that is just really kicking butt, if I do say so. And then about 1/3 of that is industry-only money. We then commit to academics on a 3 to 5 year time horizon, because less than 3 years is not long enough. More than 5 years, you need to recompete. And then we engage those 3,000 scientists and engineers, and we measure our progress. And in a very industry relevant way, we measure the technology transfer and then the number of students that were hired into the companies that are part of those endeavors. And so last year, we had 376 instances, recorded instances of technology transfer into our member companies. Note that's probably not 100%. I will never know all the stories, right? And then we had 299 hires, which is approximately 65% of our eligible student base going into the semiconductor industry. So really doing really well, especially thanks to social media, which then can transmit to the students why they should work at these amazing companies. Now, one of the things that changed with the death of the ITRS in 2016, that was the International Technology Semiconductor Roadmap, is that there's really an emphasis for a need on systems level thinking. And what I'm not saying is that you should be an expert individually in each one of these things. I'm saying you need to understand if that spin-based device you're trying to make is going to be a sensor, a non-volatile memory, or a logic switch, and then be working in an integrated sense to achieve that objective. Now, this is difficult because it's complex. We have, if you have ever looked at the difference between an ECE and a CECS mindset, if you walk into the to the university and you ask the students in ECE, are you an electrical engineer or computer engineer, they instantly are divided linguistically, right? Think about that. So you've got different languages. I mean, this is a nightmare. And you've got to get different departments working together. But it's really about driving that materials process into the right systems, meaningful systems. And so it's not about diluting your area of specialization. We need content experts, but it is about collaborating through teams to drive the right objectives. And so the first thing that I had to do back in about 2015 or 16 was to prove to folks that we could actually set out on a grand challenge and do something bigger than the sum of the individual tasks. And so through the DARPA program, we set up a comms, it was actually called Comm Center, but a comms center, and we put our sights on a massive MIMO test bed at 140 gigahertz. Now this center is doing diamond deposition, it's doing next-gen devices, it's doing materials, packaging, integration studies, all that are academically worthy, but it's also then building systems, vetting the architecture and the coding paradigms. And we did get a working demonstrator at an SRC company in Dallas, Texas. And so the advisory board said, well, this is great. We want more of this. We want these big bets on demonstrator platforms. Note, I'm not saying prototyping. That's the next level where you take the demonstrators and you take them to multiple units and you debug some of that work. But these demonstrators are really important, and they're important because they get that cross-disciplinary interaction. They get the 5 generations working together on a shared goal. And so in these kind of ways, we are now 42 years of self-sustaining, where I pointed out that we did $100 million last year, and I'm proud of that. But maybe what you don't know is that for every dollar we put into SRC, we put $15 into the academic institutions, right? So we're fighting daily for academics and their needs. So the 3 pillars is my next topic, and these are the 3 things that we must drive through the decade or we will fail. And note, if we just develop the technology and we don't focus on the people, that's a loss. So this is basically my board interview for the SRC CEO job. What am I going to do in the next 10 years? And this was in 2020. So the first is, I mentioned that the ITRS was dead. Well, this world is adrift because we don't have a roadmap. So we are working to rebirth a meaningful roadmap that everybody buys into, and we can stop saying, well, let's create a roadmap committee and start from a blank sheet of paper, and then we'll figure out what to do. That's going to take 4 years. We know what to do. It's not perfect, but it's a great resource. And that calls for 3x increase in R&D funding every year throughout the decade, starting in 2020. So we are now 4 years behind with no added funding. The next is the people. We have an, on average, age 57 white and Asian man community. That is a wonderful community, but we need that turnover in what the next generation is, and the next generation is more inclusive and more geographically distributed, and we need to engage all of them and support all of their ideas and get more women and get more U.S. citizens, and we need to create an intentional pipeline that's robust all the way from community colleges to postdocs. And then the last thing is we have to start working harder on energy and process sustainability because it's important, because the companies are at full speed trying to compete on today's front, and because this will help us win the hearts and minds of the next generation innovator, right? So we've put this into place throughout 2021, and we've now invested $350 million in these 3 criteria, and will continue to do so. But, you know, I'm at school now. It's 2024, so let's call this the midterm exam. We're halfway through the decade. What have I done? Well, I think we failed here, and we failed because I still go to meetings where they say we need a roadmap. We failed because we're not putting enough investments into those and then holding ourselves accountable to the goals, which is SRC's next step. So I'm not done. I'm going to be an A student in the long run, but right now we're failing. The next is we're failing the people, right? I have invested no additional resources over the status quo. I still have essentially the same 1,500, 1,600 folks. Now, we're doing a better job of trying to get these criteria met, but it's a handful of people. It's not the mass movement of 3x the people. It's not the intentional pipeline through community colleges, bachelor's, master's, PhDs. And then, you know, there's no doubt that we need to make faster progress on the environment. ChatGPT is consuming inordinate amounts of energy, right? PFAS is not going anywhere. So we've got to tackle those two things at a minimum. So it's not much, but it is up year over year. And so we have a solicitation for $13 million that'll come out in Q2. And I want to make sure if there's academics here that you're aware of this. Cash App, can you raise your hand? So Cash App is a program manager over there, and he's aware of this, but in the April-May timeframe, there'll be calls for these 5 topics to submit your ideas for a 3-year project at $105K per year or more. All right, so how do we view the pipeline? It's important to realize this is my perspective. It's honed on 20 plus years of semiconductor R&D and actual execution in each one of these buckets. But, you know, we have MRLs, we have TRLs, we have 10-point scales, we have all this stuff. You know, I think it's very simply, we have basic research, applied research, early high-risk development, and then we have demo and scale that's anywhere from 1 to 1 billion parts. And, you know, what we're trying to do is to engage both the academics and the companies, small, medium, and large on both sides, and get forward and back propagation of emerging state-of-the-art, crazy ideas that are improving and need to move on, or things that need to prune. And so our focus is really on, I'll say, doing what we do now, which is applied research, hopefully getting more basic research in time, but doing applied research, and like Bill Chappell did with the Electronics Resurgence Initiative, to really graduate those into speculative, high-risk, high-reward early development. There's a real hole there in our companies to have that appetite for speculative development and risk. So one thing that we all benefited from in the first 40 years of the SRC, and I'm not saying that the other CEOs were luckier than I, but was the ITRS, the Technology Semiconductor Roadmap. So in 1984, the 10-year goals for SRC eventually became, with SIA's partnership, the Microtech 2000 roadmap, which then launched Semitech. So we're in an echo here, in a sense. That became the National Technology Roadmap for Semiconductors. And it wasn't long before that became the International Technology Roadmap for Semiconductors. And that worked really well through 2016 with big bets, a new division in DARPA looking at microelectronics, big bets from NSF and NIST on beyond CMOS. And that worked all really well until 2016, when we moved from the 2-dimensional scaling era to 3-dimensional heterogeneous integration, led initially by DARPA's Electronics Resurgence Initiative and the DARPA program that I was fortunate enough to run at SRC. SIA put out a really thoughtful document called the SIA Blueprint, which justified a need for 3x increase in investments and workforce. So again, 2019, we're still saying the same thing, 3x more. And then we put out an effort to create this decadal plan to help people understand what the grand challenges, the seismic shifts were that needed to be invested with those added resources, and what are the ways that we can do this. So when I look at the nation, I see essentially we're really great at basic science, and we're really great at driving Wall Street success. And what we have is a hole in the middle where we don't perform applied research, and we specifically don't have any applied research capabilities as a nation in mechanical engineering and semiconductor packaging. We do have some in microelectronics and semiconductors. And then we have, again, this weak appetite for any kind of high-risk early development in the industry sides, right? Doesn't matter if you're small, medium, or large company, there's a hole there that needs to be filled. So again, I mentioned academic-led and industry-informed, graduating to industry-led and academic-informed. One of the things I often see is that, the companies are happy to take the project, but they don't keep the academic involved. Well, think about that. That's heartbreaking, right? Plus, you're not using all the resources you have to tackle that problem and move it faster. So what's really important to understand, okay, we do have lawyers, so I call you to the top here. Open IP for basic, going all the way through exclusive IP and revenue models, right? If you are doing something crazy different than that, good luck. It's going to be difficult to find success in a legal construct. But once you start thinking about these things, you're building up the background intellectual property. You're building up the foreground intellectual property. You are restricting the engagement model to flow in that way, and then you're requiring bigger teams and more resources to move to the right-hand side of this equation. So another part that we invested in with that DARPA program was really, well, what does it mean to do 3D monolithic integration, 2.5 and 3D heterogeneous integration? So we invested in a center led by Notre Dame to really start to tease out some of the questions as to where it made sense to fold the circuits, to bundle IP in a 2.5D arrangement, or start to do mix and match integration like DARPA is envisioning with some of the NGMM solutions. All right, so I want to dig into the technology plan, help you understand how the decadal plan evolves into the MAP, and how we see the CHIPS R&D office playing in that, and then talk about low-dimensional materials in particular. So this is the what, this is the systems we need to build, and we had 181 experts from 81 organizations, both industry, government, and academics prepare this. And it basically comes down to 5 seismic shifts or 5 grand challenges. The first is that there's more sensors creating data than humans can actually digest. So we're actually in a sea of noise, a data deluge. And we need to figure out how to turn that into an actionable intelligence rather than just be sensing and storing all the information. The second is actually that cat videos and ChatGPT are going to consume all of our available silicon based on memory technologies. And so if we don't find smart ways to store and create memory that meets the demands of the future, we're actually going to run out of silicon. The third is that our communication capacity and data transmission is really at a mismatch from each other. So we have to find smarter ways to move information and have federal learning, compute in the elbow in a sense. We need hardware security to be met. Unfortunately, hardware security and sustainability are 2 things that nobody ever wants to pay for. So it's equally vibrant to keep it at the forefront of all investments. And then the one I'm going to spend some time on is compute energy versus the world's total global energy production. So when we first put the decadal plan out, we were trying to ask ourselves, well, how do we know if it's been heard, if it's been seen? Well, IMEC is the gold standard in the semiconductor world, and so within a couple weeks, they were giving a talk saying, hey, this seismic shift on energy and compute is amazing, so all right, that's evidence of successful outreach. And it's kind of tricky to see here, but there's, on this axis, logarithmically, is the compute energy per year, and that's using every advance we have in energy efficiency, right? And on the bottom axis is time. So, maybe we're off by a year or 2 either way, but basically this is saying that the human appetite for computing and communications is insatiable, and we're going to quickly become a significant Pareto on energy. All right, well, let's think that through. Either we don't have enough energy to dedicate to compute and communications, so it stalls, or it starts to become a game of who's got the energy to do compute and has compute and communications resource, the haves and the have-nots. Either case, that's really bad for the economic prosperity of the world. So what we're saying is we need to figure out a way to get compute down in here, reset it by several orders of magnitude, and that's not going to be easy. So Mark Papermaster gave a talk at DAC the following summer, and he pointed out something that, we've done a great job with highlighting this issue, which of course not just about how the energy is used, but it's again about its impact on the planet. So trying to come back to that sustainability part. Now what we didn't do by design was put how to do that in chips and packaging. And the reason is because we kept getting a very passionate ITRS community that said, it's femtometer line edge roughness with next-gen EUV, here's the ITRS 2.0, right? And that's not the answer. So what is the answer? Well, NIST's manufacturing office, the office that runs Manufacturing USA Institutes, commissioned us with a grant to explore that with the community. And so we spent a little under 2 years with 298 participants and 112 organizations to spell out what was required in chips and packaging and microelectronics and advanced packaging technologies. And there's a chapter in there on the workforce development as a critical enabler. So it's really hard to get 300 people from 112 organizations to agree on a circle because it conveys a sense of community and holistic objective. It may also signal to the non-male world that we're open for business, but we were able to get a circle as our overarching theme, and right there in the center is workforce development as a critical enabler. Now, we put it out on social media, and I'll talk about that in a second, but the key point here is that this roadmap is focused on sustainability. Sustainability for electronics on energy, on the environment, and on the people we need to do this manufacturing. So we put it out on social media, and this is how the world wanted to see it, in boxes that are layer cake, very electrical engineering mindset, so that's great. So we're trying to talk to different worlds. Again, it's the French and the Italians debating whether beaches, wine, and cheese are nice. And Chapter 11 is workforce development, and I'll be darned if the first comment on social media wasn't, workforce is number 1. Why is it Chapter 11? So in that document, I want to go through a couple things. Let me check the time here real quick. Is that right? Oh, we did, okay. So it's 9:10? Okay, all right. So in that microelectronics and advanced packaging technology roadmap, I want to march through a couple high-level things, and we'll dig down into the materials that you all actually care about. The first is the application landscape. So remember, I talked about the drivers, the application system drivers coming from an educational need, right? From the decadal plan. We've infused those into this document so that the technologies are pointing you in the right direction should you consume the document. And the current drivers in the next couple years are really generative AI, that's no surprise. The electrification grid, right? So silicon carbide and gallium nitride are hot to trot. And autonomous vehicles. So that high frequency communication center is probably going to do more good for LiDAR than it actually will do for 6G comms in the near term, which was on our mind, but that was not the point of the grand challenge. As I mentioned earlier, there's many more sensors than we can actually consume the data from. Now, this was always part of the calculation. 5G is machine-to-machine conversations, but it's still data. It's not actionable insight. And security is a must. And then what we see, and I think this is part of the reason for Commerce's investments in Global Foundries for automotive and defense parts, is that the key technologies in the space, 22 to 65 nanometers, are in shortfall. They've not been built out to accommodate the growth in this sector. On the sustainability side, we really need, a several order magnitude improvement in energy efficiency. And the Department of Energy is hoping that the and science portion of the CHIPS and Science Act gets some funding so that they can help participate and commit to this important energy efficiency element. Advanced packaging is going to bring closer coupling of various architectural blocks. So if you think that general purpose compute is just either a CPU or GPU, that's incorrect. There are NNUs, XPUs, FPGAs, memory, photonics coming online, all of which need to be co-packaged, first for high performance computing and then eventually to trickle out into other areas. I think SK Hynix is talking about putting a facility outside Purdue for HBM attached to GPUs, which is a really great win. This blew my mind. There were 5.3 billion cell phones thrown away in 2022, 60 million tons of e-waste, very little of which was recycled. And so, designing for sustainability, integrating sustainability into your mindset. And one thing the committee said, hey Alex, one thing the committee said is that industry should lead and can lead faster than government on this front, right? So don't wait. On the technology side, I remember the dialogue was analog's going to die at the hands of digital. Of course, now I'm telling you that sensors are outweighing human ability to consume sensor data. It's really a mixed signal world, right? It's a mixed signal, 3D heterogeneous integration world. That's our future. And so really, how do we couple those ADCs and DACs and bridge that space efficiently? Those that know are kicking butt, like AMD. And those that aren't there yet, will continue to lag behind. Power conversion, power delivery, thermal, darn that entropic law, is really the challenge for everyone. And so there's a universal need for thermal management, thermal solutions, the rise of mechanical engineering again. Wide bandgap materials and photonics are actually on the rise, and I worked in 2007 on an Intel integrated photonics project, was just still to this day the coolest science I've ever done, but the timing was wrong. Photonics is taking off. So if there's a space where there's excitement and a lot of capability and space for new and expert ideas, I think photonics is a really interesting area, and it's one that the Industrial Advisory Committee called out as what could be a competitive advantage as the investments come online in the United States. Now, what are the needs? You need a PDK or an ADK for packaging that also considers 2.5 and 3D dynamics, considers increasing standards around shared solutions. And then, what the researchers would really like is a research development kit that they have some flexibility to play with, but don't have to renew or recreate the wheel every time, right? The key question that this roadmap asks is, okay, everybody can now see chiplets as an emerging future. What's after that, right? And it's a good question that I don't think everybody agrees upon. So let's dig into low-dimensional materials. And I probably don't need to spend a lot of time on this, but I thought, depending on people's perspectives, a quick primer on 0, 1, 2, and 3D materials made sense. So if you're looking at carbon, 0D is fullerene, 1D is a carbon nanotube, 2D is graphene, and 3D is graphite. But what do the zero-dimensional materials do? They really confine the phenomenon to the small scale, to the nanoscale. So quantum dots and nanomaterials really fit into that bucket nicely. On one-dimensional materials, right, they're now extending in a single axis that phenomenon, giving them, distinct mechanical, electrical, and thermal properties. These are carbon nanotubes, conductive polymers, some of the graphene nanoribbons that Zafar has been working on in conjunction with several schools. I think you picked that up at UC Berkeley. The two-dimensional materials extend in bilaterally. These are graphene, which up until the other day didn't have a band gap, and now Georgia Tech is claiming a significant breakthrough in their graphene. The transition metal dichalcogenides, or TMDs, like moly disulfide, tungsten diselenide, the mixines, oxides, nanofilms, etc. These are really phenomenal if you can overcome that darn van der Waals contact and get the right arrangement of your materials. And then three-dimensional materials are really, looking at, in some of these cases with nanomaterials, using aggregates, mixtures, composites, and trying to get some of the benefits from 0, 1, or 2D in more of a bulk type structure. And what I want to make sure that this community understands is, I know the conference is called 1D and 2D nanomaterials, but 0 and 3 are equally interesting and important. So, for a given application, there are needs in all 4 of these dimensions. So there's a nice preprint that Zafar, I know, is an author on 1D carbon materials for future computing, and I thought it had a nice diagram in there on both how these kinds of materials can be useful for electronics, for spintronics. There's also some really lovely work at Purdue that, sorry, names are my kryptonite. It is Zihong Chen and her group have done to show that these materials can serve as a barrier or as interconnect solutions. Of course, people have been looking at carbon nanotubes for interconnects for a long time. I'm glad I'm not the one that has to pick them out and put them all in the right place and make sure that the polydispersity is meeting industrial specs. But there's a lot of interest in these various topics for transmitting data, for operating as a switch, be it a logic, a memory, or a sensing switch. So Zafar, I think we first met in maybe 2012 or 2013. It was a long time ago, back when he was a young student at Riverside under Professor Ozkan. That was part of the StarNet DARPA program. That is why I said hi, Alex. Really at that time, some of the question was, okay, graphene doesn't have a band gap, so what can we do with these TMDs and benefit from the band gap? And we were looking primarily at going beyond exfoliation and taping things down to get an IV schematic, and looking at growth, looking at defects, looking at oxidation, looking at different variants. What he learned there, I think in this early study, was really that the regrowth step in a sulfur transmission across moly oxide template really controlled the quality of the crystals. And so I took out sort of 2 pictures. These are just 2 growth conditions, and it's phenomenal difference in the quality of the moly disulfide growth. And of course the challenge at that time was, well, can you grow it and contact it and match the exfoliation results? And what the world is seeing is, well, that's really hard. And I believe the best results that I've seen that are sort of industry relevant are based on a transfer process out of IMEC, where the wafer is grown and then transmitted to the carrier wafer. Now, more recently, he's been digging into, after his Riverside and Berkeley postdocs, where I believe you met Professor Cromie, right? Been digging into these graphene nanoribbons, and recently awarded an SRC project to work on this. And what we love about this is that he is collaborating with different institutions to get the right perspective of device, materials, mechanical properties, characterization. And UC Berkeley is an amazing school, but we often forget that Rochester, Colorado School of Mines, Riverside, these are equally amazing schools and contributors. So the graphene nanoribbons, as I understand the armchair one, has a really great approaching theoretical current limits, and that really now it comes down to, again, making contact to these darn van der Waals materials, and then integrating that into circuit level demonstrations to show TSMC, Intel, Samsung collaborators that this should be on their roadmap, right? Now, their understanding is actually accelerating pretty quickly. So there's a really nice study out of MIT and TSMC from 2021 that I would point you to, where the short story is they learned that beryllium makes a really nice contact, but it's the fundamental understanding of how to do that that's really the key part. And then I believe from IEDM this last year, Kevin O'Brien's team presented essentially a side-by-side comparison. This is Intel, yeah, sorry. And they presented sort of side-by-side comparison of a gate-all-around structure versus a TMD-based solution. And, for me, I don't get enough time to do science anymore, but this TEM with the tungsten diselenide and then the distribution, it's just beautiful, beautiful work. So what does industry need for this space to mature and really go head-to-head with the gate-around devices? Well, it's the contacts, it's the channel growth and understanding, it's the gate oxide, it's the variability, it's the doping. These are, of course, the themes that always come about for the devices. But on top of this, you're growing these things laterally at specific dimensions with high quality. This team of authors in both of these cases is somewhere near 30 people with millions of dollars of resources to their avail. So my hope is that the NSTC can become a playground, the ME Commons can become a playground where some of the academic questions can be answered with a little more vigor. When we look at the map, there's several chapters that call out materials, but there's two that I wanted to insert sort of the condensate slide in here. And one is actually the material substrate supply chain folks. So my argument would be these are the equipment and materials providers that are making the foundation for the chips. And what's important to understand is that it's not just general purpose compute and one ring to rule them all. It is now, again, these application-specific drivers that change the material needs. If you're working on gallium nitride, then a gallium nitride organometallic precursor deposition is really interesting, but it's a lot less interesting for the silicon folks. So just looking through here, I think that for the 1D and 2D worlds, there's opportunities in 3D monolithic integration. There's thermal and electrical solutions, getting higher speed performance regime. I'm hoping to hear some from you on that, Ali. Moving into high frequency miniaturization, right? These are the strengths of the 1 and 2D community, but you've got to be going up against the emerging state of the art and the incumbent, right? Another chapter that is really closely tied with materials is the metrology element, where, again, unless you can get those atomic scale characterizations that Intel had just gloriously in that paper, you're going to be hard-pressed to turn the crank in a meaningful way. How do I go back? There we go. And then, there's opportunities that I've mentioned for materials in the memory, in the magnetic space, and I believe there's some opportunities in harsh environment type thinking. So, all right, that was the technology space. We had the decadal plan, which is the systems to solve. We've got the mapped, which is the chips and packaging together, and now we need to turn to the people. If we develop the technology and we don't have the people, it's just going to go offshore, okay? So this is a really nice Wall Street Journal article that condensed a lot of thoughts down into one nice graphic and one nice quote. So you can see there's a big red purplish square there in Arizona. And Secretary Mondo is calling for a doubling of the workforce, which requires the university academic systems, the colleges, to triple their commitment and their student body. So again, 3x. 3x the money, 3x the people. This is now from the Microelectronics and Advanced Packaging Technology Roadmap chapter. So the semi-jobs that need to be added by the back half of the decade, approximately 60% of those are technicians and 40% are bachelor's, master's, PhD. So the training needs to reach all of those levels in order for us to succeed, but it's not one or the other, it's both, right? The challenge here is that despite the 10-day boot camp type articles, training people takes a while. And so we're already 4 years now late with not training people. Well, this is just nonsense. So another part that's really important is we can purchase talent. I will tell you, as an organometallic chemist, I was trained for oil and gas. But Intel sure looked like a whole lot more fun and was paying better, and they had a signing bonus, and Portland seemed cool. That is why I joined the semiconductor industry at 28. I wasn't a 3-year-old that wanted to be a semiconductor engineer, right? And I got amazing on-the-job training from Intel, and I miss my colleagues. They're fantastic. But money drives people to make decisions. I'm not saying you have to pay outrageous fees, but it's part of the calculation for smart folks. Smart folks are also expensive. You need both the talent factory and the talent marketplace. If we train a whole bunch of people and then we don't have jobs, well, what are we doing? Right? So you need to be driving both of those equations. You need to be putting people into jobs, be creating jobs, and then making sure that those that want to participate in this pipeline can, no matter what their journey or origin is, right? We spent a lot of time on knowledge, skills, and ability, and I'll dig on that in a second. But what we as a group believe is that abilities are better than knowledge and skills, and that's because especially in our industry, it's constantly changing. If you don't have the abilities to size up what's happening and how to go forward, if you can't live with ambiguity, you're not in the right industry. Because what it was like in 2000 versus what it's like today is night and day. So I can't just come out with a degree and be done for the rest of my life like maybe a banker can. So knowledge, skills, and ability are not equally weighted. Abilities are critical. And then something I think that's really a problem here is this has to serve industry. So they have to help define it. They have to hire people. But who owns this? I mean, really the universities and the colleges and the schools are the owner, right? So there's some tension there between who it serves, the actual workers, the companies, and then who is asked to carry that lift. So one of the questions we often get is, well, what is a semiconductor engineer? And the answer is it depends on where they go to work. So NVIDIA's needs are very different than TSMC's needs. And it's not just ECE. So one of the things I don't like about the workforce development discussion is it's a bunch of deans from electrical computer engineering saying how they should just get all the money and they'll do it. But we need, honestly, if we're going to fall in love with manufacturing again, we need to win the hearts and minds of the mechanical and the chemical communities, more so than the ECE communities. And we need to put money in so that they're not all going to bio and batteries. Right? Because I get thousands of applications to train people, and I accept about 5% of those awards, and 95% of them go to bio and batteries, because that's where the money is. That's where they get their support. So we do need a 3x commitment to ECE, but we need a 2x more commitment, a 6x commitment to materials and mechanical engineering. We got to get through to them as to why it's important for them to get involved. These are the knowledge, skills, and abilities that I mentioned, and it's a little bit of an eye chart, and there's actually more details out on the web page, but to call specifically, So if we take like Zafir's group on device circuit systems here, you can see that having that system-based mindset is on the rise, right? And if you go way out to the right, having a chiplet advanced packaging understanding, that's where the infusion needs to come. So what I see generically is we need to be training folks a little bit more about statistics and how to use that in their experiments across the way. We need to get materials and mechanical engineering infused into the ECE curricula. We actually need to embrace the generative AI and how to use it as a tool and what it can and can't do. And then work on collaboration and selling your idea. I've seen thousands of really good ideas that go nowhere because they can't be transmitted to somebody that would support or help raise your effort. But beyond that, this is when I look at the next generation. These are some students or scholars that I've personally known. And, I think what's important is to help them understand we need to drive these holistic solutions, and that the magic in their phone, this is EUV. It's already commercialized right here, which is really exciting for me because I was on that in 2007. But we need their help. These are hard technologies. We need their ideas. We need their energy. Right? We can't do this alone. Having the mindset of that's top secret information, I can't tell you anything about it, it's not working for the Department of Defense. It's not going to work for the semiconductor industry. Right? We need their help. We need their ideas. And we need to take a chance on them. Some of it's going to not work out. Some of that you may have seen in the past, but this is a different time. We need to help them understand that they're going to have successful families. They can send their kids to college, and they can have a retirement based on semiconductor employment. We need to create internships and back and forth opportunities, right? This is really tough if the companies aren't willing to share any information with a prospective hire. You've got to trust them. And we need that aspirational new narrative. And I think that aspirational new narrative is they know there's not another planet. They know that Mars and the moon aren't going to be here fast enough. And if we're doing anything that's faster, cheaper, smaller, throw it away, they are going to go to bio and batteries. So we made a commitment to sustainability, and the basic gist is that energy efficiency, seismic shift meets, I'll say, PFAS, greenhouse gases, water, and energy use in a factory. And there's a lot of good work to do there. And so each year, I publish 2 open letters, one in April that's about our progress on the people, and one in October that's about our progress on the planet. Definitely, if you have any questions or you want to understand where those are, don't be shy. But we're not moving fast enough. That's why I give myself interim failure. All right, so what's our call to action? Well, a little bit of this involves the CHIPS Act. And so we talked about the what is the systems. We talked about the how, which is the chips and packaging, including the workforce. And now the implementation is, quite frankly, the CHIPS Act. So both of these documents have always been envisioned to be bigger than what SRC can do alone. We're going to use that to engage with the community, to hold ourselves accountable to whatever we can do. And hopefully, Deirdre doesn't start from a blank sheet of paper and create a new roadmap, but rather take this, use it, use us, whatever. This is the echo was the SRC 10-year plan grew into the NTRS and the ITRS. That was not just SRC. That grew and had a life bigger than us, right? So when we look again at this pipeline, this is where we're at today. We have the big DARPA program that then feeds into the DARPA Electronics Resurgence Initiative, or now ERI 2.0. That feeds other programs like SHIP and RAMP-C, which are 2 of the more widely known defense initiatives. And then we have the industry funds in what we call the Global Research Collaboration. We're still very much global. We're very much US and like-minded nations, and very proud to have TSMC, Samsung, SK Hynix, NXP as members. And so when the CHIPS and Science Act was signed, we sized it up. We said, well, what should we be competing for, and what should we be partnering with people on? So there was the the Emmy Commons money that the Department of Defense got, and kudos to Arizona on the SWAP hub and participation, and best of luck getting that off the ground. And then when you start to dig into the 9906 investments for R&D, there was the NSTC that Deirdre Hanford is now the CEO of at NatCast that is moving forward. There's the advanced packaging manufacturing program, which includes a packaging prototyping facility, or APPF, which will, my guess, based on what I've seen out of Commerce and IAC, will be a resource for the NSTC to get some of its things packaged. That is a junction or union between the NSTC and the NAPMP. There's the NIST metrology program. I think Paul Hale is here from that program, and they're off the ground running with some investments that they had a workshop on late January, early February, and they're off to a great start. And then there's this CHIPS Manufacturing USA Institute, and I'll talk more about that in a second, and workforce development. But if you want to think of it this way, SRC is aligned to NatCast and IAC leadership on the NSTC and the NAPMP, and trying to make sure that we can, feed or follow that. And then our focus is really on the Manufacturing USA Institute and the workforce development. And so what do I hope SRC evolves into this, where there's a Manufacturing USA Institute that basically grows our commitment to advanced applied research, and then has that carry over into early development, a la the ERI type model, and is bridging that university to industry handoff and participation. And so what is that CHIPS Manufacturing Institute? Well, there was a notice of intent that was released in late January alongside a notice of intent for the first phase of the packaging program on materials and substrates. And this really builds upon a request for information that Commerce put out on manufacturing institutes that we submitted to, as well as a December 2022 workshop on digital twins. Note that the digital twin is what a lot of people have locked in on, but I would argue that in order to have a meaningful digital twin, you need to have a physical twin. And so I think of it as sort of, it's digital and physical. And they pointed out that this is for semiconductor manufacturing, packaging and assembly, and the validation of that in a prototyping facility. Right? So we've got the M, we've got the AP, and we need to bring the design and the digitization and the access models together. And these activities need to include having a facility where experiments can be run. So this is not high volume manufacturing where you have no ability to pull levers, and where proprietary information can be preserved, right? So that maybe frenemies can collaborate in one place. So it's expected that NIST will commit $200 million over 5 years, and legally a one-to-one cost share is required. A higher cost share is probably going to be part of a winning bid. And we're looking forward to the NOFO coming out. On our website now is this page, which is our team for the Manufacturing USA Institute, which well, it's on the web, so it's public, but we're calling the Smart USA Institute, so it's the Semiconductor Manufacturing and Research for Twins USA Institute. We have over 50 partners now, which includes 5 national labs, 4 nonprofit partners, 13 academics, and the basic arrangement is that SRC pursues government funds and large industry funds, and the academic partners pursue regional and state funds. So if you'd like more information, I've put the links there. Now that will mesh. This is my version of the document. There's other Commerce documents that I refer you to for their guidance, but that meshes with the NSTC, the NAPMP, and its piloting facility, the Emmy Commons, where I'm actually hoping that some of our DARPA-based work can graduate into those capabilities in time. And so this is how I see the CHIPS and Science Act, and what's important is the and science portion is also needed, right? So there was $200 billion that was allocated but not appropriated. The Department of Energy and NSF are working hard to justify that they should receive those funds from the taxpayer. I don't think they're going to get there this year because the the taxpayers distracted this year. But ideally down the road, we've made a more significant commitment to energy, to science, and SRC can benefit from fueling its investments in basic science, because right now we're just taking the dollars and we're moving them to an area we think is more important, and all we're doing is robbing Peter to pay Paul. So we will cheat basic science with the precious dollars that we have if we don't backfill some of that stuff. So in summary, 3x annual increase in workforce and in technology. Cash App, I pointed out earlier, is a program manager here from SRC, so feel free to chat with him. Novel materials are critical to all that we do. The decadal plan took us 5 years, or the decadal plan and the MAP roadmap took us 5 years. So, as an advocate for science and as a taxpayer, I do not want to lose that 5 years' time to new road mapping activities. Take it and go, right? It is a living community. They meet every Friday. If you're interested in finding out how to join that, you can let us know. We will refresh the document in September of 2025 on a 2-year cadence so that it's capturing all that we know. It is how we are measuring ourselves. It's how I'm measuring myself to the board. I've mentioned the $13 million solicitation that will come out this spring in 5 topical areas. We'd love to see some materials and integrated manufacturing studies from all departments there. And so if I leave you with a call to action, it's that the 2D scaling paradigm will not work for compute and communications. This seems obvious now, but when we started in 2015, nobody was buying it. And that's how long it took us to get to this point, right? I believe the future is in microelectronics and advanced packaging. And if you forced me to rank that, packaging is number 1 and devices are number 2. And I tell you, the device folks don't like it. They do not like being demoted. And the packaging folks aren't ready for the attention they're getting ready to receive. We've got to work on a fast fail and technology transfer mindset. And that's hard because it requires discipline, it requires goals, it requires the right partners. It means some stuff's not going to work. That is science, right? Remember when science used to be about I learned something from a failure? Now it's always bright, shiny object got on the cover of Nature and give me more money. Our nation is broken on science innovation. We've got to work on people and casting a broader net of what that means for who's involved. And we've got to work on energy efficient systems and eco-considerate manufacturing. But what I try to convey, especially to scholars, is there's a really bright future here. This is probably the most exciting time in 25 years of semiconductors. So what we need their ideas, we need their energy to be successful. So I think I did all right, thanks to the early start. I'll be happy to take any questions, or we can just start the break. So you may need, there's people online, I think, so you might need a microphone. Sorry. And I might need to stand closer to the mic.
Thank you.
Now that I say that 45 minutes later.
Todd, great talk. Mike Berkland, Raytheon here. So I would say you guys have set the table really well, laid the foundations, SRCSA. What does this time next year, what needs to happen from execution or what you want to call success? Where do we need to be to retain the momentum and the enthusiasm? I mean, and it could be workforce or whatever, not necessarily a brand new invention that comes out of anywhere, but what do we need to show?
I think it's 2 things. I think we need to make some noticeable action on workforce. I think the states and the schools are moving forward without government support at this time, which is noteworthy. There's sort of 5 regions that I'll say are doing better than others. Arizona, Texas, Florida, I'll call it Indiana, Ohio, and New York. So whatever regional efforts can just get that off the ground on the people side is 4 years overdue. On the CHIPS Act investments, you know, the Emmy Commons are going to be a good investment, and the NSTC is the flagship. The NSTC announced that it was going to make some investments in workforce as one of its first actions. So I'm excited to see that come to fruition. But I really think for this group right now, if you're not involved in that community of interest for NatCast, NSTC, you know, don't come back and complain later that you didn't state what your interests were or you didn't, you know, get in any resources. Now's the time to get involved. So I'd start there. I'd start with fighting regionally for workforce and getting involved in the NatCast community of interest.
Hi, thank you. Hi, everybody. So my name's Kathleen Melda, and I am very fortunate 15-year PI for SRC work. So I very much appreciate it, and I'm also proud of my former students. So I have 2 questions. I have one comment. The College of Engineering at University of Arizona has been very successful in hiring faculty across lines. So we have people in material science who actually got their degrees in electrical engineering and similarly. So I think that's just a natural. But here's my big question. So how can we increase the funding per project? When I hear the $105K per year per project, that's about the same funding that we had 14 years ago for projects.
Yep.
And that is, there's a couple things about that. That's a barrier to collaboration.
Correct.
And the other thing is, right now, the way that the U.S. technology is going, if we really want to get the best talent, as you gave in your example, we're going to need to pay for that best talent. So I hope that we can have a discussion on that.
Yeah, I'm happy to discuss that. I think that's really critical. You know, especially in a hyperinflationary environment where the universities and colleges are creating long-term value, of course they're going to be more costly than inflation. I'm really proud to say the first thing I did when I joined SRC in 2016 was push the size of the award on the DARPA program up to $250K per year per faculty. So that was great. I was able to do that because of the government amplification. That program is now approximately $60 million a year, and we still get complaints that there aren't enough faculty in the group, so there's always that dynamic, right? Oh, well, just, you know, get us more people. Well, there's a budget, and if we want more dollars per person, you know, you have to be mindful of that dynamic. I don't have a congressional budget. I'm sorry. On the 105K you mentioned today, actually, when I came in, I pushed that up from 87. And 2 of the topics that were listed there are actually 135 and 150. So that unfortunately is not fighting back the inflation as fast as I'd like. But I think we need to invest in the right ideas and the people that want to do that, and draw a cut line a little harder. Not everybody's going to be able to participate. So that's the short answer. Yeah.
Hi, Todd. Fantastic talk. Sam Eaton, Department Head of Material Science and Engineering. Super excited to hear you say that, you know, we need a 6x investment in material science to really help create the next generation of design enabling materials to support the microelectronics community. So I see that, the SRC is very much interested in 0D, 1D, 2D, even 3D materials. A lot of the precursors for 2D materials will also hopefully transition to the realization of quantum devices. I didn't see that really being mentioned in the roadmap. Could you maybe perhaps elaborate on that?
Yeah, a couple things to try to be as honest with this crowd as possible. There was a separate quantum roadmap run by the QEDC consortium at STI, and we tried not to step on their toes and to complement their document nicely, so I refer quantum enthusiasts to that effort. Quantum is also extremely well resourced by the government relative to its immediate return on investment. So I'm trying to get the world to fall in love with electronics, or with electrons, magnets, and photons again. And the quantum stuff is resourced appropriately. The third item is quantum's not pre-competitive. Quantum's extremely competitive. And I don't serve the competitive space. I serve the pre-competitive collaborative space. So that would be my three answers there.
Thanks. Thanks, Todd. Aaron Franklin, Duke University. Great perspectives, and I have to ask the question of kind of the elephant in the room, which is your avoidance of the IRDS as roadmap criteria with IEEE backing.
Yeah.
I know as an academic, we certainly have had sort of a ready jump from ITRS to IRDS. So just your comments on where that slots in from perspective building on funding and future.
Yeah, I'm not terribly familiar with what's under the hood of the IRDS. It's been a long time in the making, and not all of it is publicly available. So when we set out to build this information, we did build upon the heterogeneous integration roadmap as a standard, and many of the folks that were involved in our effort were involved in making and propagating the heterogeneous integration roadmap, so we've definitely stood behind that. The IRDS has been more in flight, going through this long machination of what's the right product to put out, what's the right message, and so it's not something that we could build upon. It's not at a state where we could build upon it. Find people in good work, I'm sure.
Hi, I'm Rojin Yasai. I'm from the College of Applied Science and Technology. I wanted to ask about how do you think that the security fell in your roadmap? Because you mentioned it was part of your solicitation, but it was never to be seen in the roadmap or planning.
No, and I'm glad you asked. That is not an accurate reflection of what I was trying to say. Now, that may have been what you heard. But the hardware security is critical and is in the system document. It also, let me get to, sorry. Oh. It is also here as a need and driver in security and privacy in Chapter 3 of the Microelectronics and Advanced Packaging Technology Roadmap. And I would argue there's some really exciting opportunities in packaging security that are being driven. So what I was trying to say is there's two communities that are really critical, sustainability and hardware security, and they're very passionate people, very important topics, and they have 10 cents between those two communities. So what we need to do is make intentional investments that are attacking maybe that shared opportunity where security meets these other topics and is driven into commercial success.
Well, thanks, Todd, for a great talk. So my question is exactly on sustainability and the metric, energy efficiency as a metric. So at the time of Industrial Revolution, it was the efficiency of coal engines. They got improved, but coal consumption increased. In a sense, by improving energy efficiency, we are trying to make computing more pervasive, so the energy consumption will likely increase. What is the
So
right
Javon's
metric?
paradox, right?
Yes, exactly. Brooks' postulate is what I'm talking about. So what is your take? What is the right metric to quantify sustainability? Thank you.
So your high-level question I'll leave to policy experts. But if I look at this graph as a scientist, there's two things we can work on. One is the world's energy production, and one is compute and communications contribution on that landscape. I think what we've tried to do, and we need to actually do a better job of, is helping people at the building block technology level understand how their choices impact the overall energy landscape holistically. You know, if Intel and Micron are saying, you know, my device is as efficient as it can be, it's, you know, as we push data back and forth between logic and memory, it's their problem. That's not the right answer for the system. But I don't believe we'll be successful at telling people that we should go back to, you know, no devices and caves and sticks just to save energy.
Thank you very much for a really stimulating opening talk, Todd. I wanted to ask, or follow up on your point about we've got a great roadmap here. There are even other roadmaps out there. What's it going to take for us to get behind one roadmap, and what can the people in this room do to help us with that? Because it's hurting us nationally to not be able to figure out what the priorities are and commit to them. We're doing too much peanut butter and not enough focusing.
I think at a high level, America's love for the dollar means that this NSTC and its $5 billion investment will signal to the world that whatever they're doing is moving in the right direction. Now, they have all these documents as input and many, many private conversations, and Commerce has had many private conversations. So really, it's about Deirdre and her leadership team now graduating beyond the little societies and their plans into a more of a national technology roadmap for semiconductors. So that's, I think, will be the next step, if I answered your question. All right, maybe, oh, go ahead. Yeah, please. Yeah, I was just going to say we could, I'm happy to enter. I'll be around a day and a half, so. I'm really excited to see what y'all have to say, not what I have to say.
I'm Advait from University of Virginia. My question is related to the people part of the agenda. So I'm curious, like, if new people want to join SRC in terms of any of the things that you mentioned today, right? What are some of the things that folks can actually look at and say, hey, okay, maybe one option is, okay, call for proposals come, they apply. Yeah. But in terms of new funding that SRC gives, how many of them are new to new faculty members or new universities who like to join and contribute?
Yeah,
Thank
so
you.
we have, since I took over, we essentially have a metric of new and young faculty, and we shoot for about 25% new and rising stars. And I've made intentional purpose to try to get the scholars that are in the community today to realize if they don't go to work for a company, that we're part of their academic future as they come out of school. So they're not essentially, you know, pivoting to bio and batteries because we're not part of that support. You know, we do support about 5% of the ideas we receive, and our merit line is approximately 5x higher than that. So we could, in theory, go to 5x more without any decrease in quality. As we look to the workforce, we're really trying hard to secure funds to create more fellowships and scholarships for bachelor's, master's, and PhDs. where we can intentionally support the student. I personally believe we need to push the price up to get more domestic attention. I'm not going to make any friends with deans and faculty when I do that. So I've got to find a smart way to do that. The other part is, we're trying to vie for government amplification on this objective. And again, I mentioned 60% of the workforce needs are technicians. I'm not going to serve technicians. It's mission creep. I can't do what I'm doing. We're 20% of the PhDs in semiconductors. I need 3x that, and I need bachelor's and master's integrated into that work. Other organizations can tackle the technicians. But I'm extremely interested in engaging geographically smart community colleges to look for four-year students that can come and finish into the professional class and are adjacent to where these manufacturing facilities are. So if you want to say, kindergartner to bachelor's and then sort of four-year community college to PhD, that's what we're trying to do. After a few years, we've gotten tired of waiting for the government. So we actually started a Kickstarter campaign, and we have $6,500 right now, which may get us 2 or 3 students. But, we'll do everything we can. So